All right, thanks everybody. Welcome to this second and final communication session for the Neo-Marvin Orebody case study. Been quite active in the last couple of months, finishing off the work that we started last year and presented in December. Excuse me. So we'll be recording this session for people on different time zones and who couldn't make it here. And we'll probably run through the slides. I'll get Craig to do most of that work. And if you wouldn't mind saving your questions until the end, we've got the end 10 minutes or 15 minutes or so will be for discussion. And let's see how we go. So many of you might know me from different hats that I wear, but today I am representing Whittle Consulting as the project manager. Craig Davies, my colleague, did the bulk of the work with support from Lee Lawrence and some oversight by Gerald Whittle. This is just the same as it was in the December communication session. And this is a case study piece of work that was done under the auspices of Seek International's Global Water Initiative, as you know, and it's the first step in what we're terming a meta study, exploring how to model water consumption, treatment and management and link it directly to the life of mine planning activities that go on in mining companies. So that includes the production scale, and it also should and must include climatic and geological contexts. So that was the genesis of the project. We had three starting high-level hypotheses for that. This we showed in the December session. We believe there is a link between the hydrology and the mine planning that's not accounted for in modelling in either discipline, and it should be. That material changes in water-related costs will have an effect on the size, shape and scheduling of the ore body, those so-called second-order effects, which we'll come back to. And that second hypothesis is the main hypothesis that we're dealing with in this case study. And material changes motivated by third-order issues, such as social, environmental, are nonetheless mitigated by such second-order effects. So we're going to really look at work that's aimed at that middle hypothesis, and also right at the end we'll suggest some further work that will allow us to work our way towards all of these hypotheses. So this is what we're going to talk about today. We've already done the introduction and context. Craig will take over in a moment and talk about the Neo-Marvin ore body, the scenarios, the objectives, and all of the things there, all through the synopsis of the model and the first, second order effects, and down to the observations, and then we'll talk about that extension work. For those of you who didn't attend in December, first, second, and third order effects, just a very brief introduction to that. First order is all the things that you might expect in an engineering study or a rescheduling event in life of mine planning. It's the effects concerned with capital and operating costs and calculating net present values for those. For example, related to waters might be cost of pumping water, as you'll see shortly, cost to pump water, to desalinate it, things like that. What are the capex and opex considerations there? The second order are those effects concerned with the ore body as a whole. So we're talking about how such changes in costs affect the scheduling, the cut-offs, all that sort of thing. So I've written there implications for cut-off grade or cut-off value. And then the third order effects concerned with environmental and community value of the impacts, such as carbon footprints, any license to operate ideas, and so on. So that's how we've split the first, second and third order. So where did we get to in December? We had the model together, and we'd been talking about pumping water from the coast, and we'd used Chile is as an example where they do some of this, so pumping from the coast to low and high altitudes. The water supply, we had the model operating around continental water, seawater, and desalinated seawater, and the effects of that, and that we had used different tailings practices in various modes of thickening and filtration, which Craig will expand on shortly. And so that was what we presented in December. And then since then, we have done a few things. Did a little bit of validation on the inputs, which is inherent in the work. The big thing that we did though was to look at second order effects. So in that work up to December, we'd really only got the model together and talked about first order. And in particular, the second order effects are about how the mining pits were reshaped because of changes in conditions for water costs. And we also introduced, because we were dealing with seawater, we introduced a penalty in the recovery, the copper recovery in the ore body. So that's that bottom line is what we want to present today, although I know Craig has included all of the work in his waterfalls and everything. So we'll see the whole thing in its entirety. So I see Gerald's just joined us. G'day, Gerald. I'm just about to give a substandard explanation of your wonderful rocket slide here, so you can mark me out of 10 later.
I will.
So this is the famous rocket diagram of Whittle Consulting, and it is here explaining that a mining system is a whole thing, and that there are any number of models that you might have in each of these areas of a mine. And what Whittle Consulting's process does is to combine them all in a financial model, but using the block model, the resource model, as the basis for how to value each block in the block model and in what order to mine it. And it includes all of these silos here, all the way down from the scheduling cut-off blend, stockpiling, importantly the processing, the product mix, and logistics. So it all comes together in one model. And after all of that, they famously have all of these 10 mechanisms, including the capital scaling, all in one model. And that was the basis of the idea that we would include these techniques. We would use the Neo-Marvin Orebody and impose upon it various conditions around water supply. So Craig, I'm going to stop the explanation there and allow you to carry on. Will you reshare?
Sounds good, Phil. Right. Yep, I think I've taken over the screen share. Let me know if that's coming through.
Yep, it is.
Right. So I suppose one of the reasons that I wanted to include this slide is that the traditional approach to all of these pieces is that they occur in silos. So somebody does the MET test work and says, this is the grind size we're going to, and these are the recoveries. And then people take those assumptions and build out the rest of this value chain. So the premise for Whittle Consulting's work in general, and Gerald can do a 2 to 3 day explanation on this at some point if you're interested, is that we do all these things at the same time. We build an optimization model that's capable of handling all these pieces and looking at all these options. So one of the things you'll notice here is that there's no explicit water modeling. And I'd like to be able to include that. I would like to have a piece in this that says, hey, we look at water balance, and we do that to a degree in a lot of our projects currently, but I think it could be a lot better integrated than it is. So this is really context for the work that follows that. We have built this optimization model, and we're doing pits, phases, mine schedule, cut-off, blend, stockpiles in the background of all of this work. I'm not going to go into it in any level of detail, but it's important context knowing that that's occurring. So this is the ore body that we're working with for this scope of work. So we've got a porphyry copper gold with about 2 million tonnes of copper, and 4 million ounces of gold recoverable. So that's after it's gone through the plant. And the premise for this is we've built and sized the mining fleet and the plant, and everything's good to go for this greenfield operation. And then we find out that for this 19-year life of mine, we're no longer allowed to access the local groundwater. So we had a plan. We've built this optimized mine plan that everyone's very happy with. And suddenly one of the fundamental assumptions that we can just source local groundwater is not available. Just a few clips here showing gold distribution closer to the surface, copper distribution at depth. So this is a real ore body, and it's one that we can do lots of this project work with because there's no concerns on data privacy here.
Sorry, it's a realistic but not real ore body, Craig, if I understand right. Is that right?
Yeah, I think that's appropriate phrasing to capture that. So one of the interesting things on doing this work on a theoretical ore body is we have to determine our own criteria for success. So what are we measuring by? Because if you can't measure the different outcomes, how do you know what's an improvement? So we'll discuss that a little bit in the preamble as well. So when we were evaluating what we need to test, well, first thing is, where are we getting the water? So fresh groundwater was the original case, but if that's not an option, we're either getting desalinated seawater or raw seawater. So obviously all of these things have implications. You need to build a desal plant. And then we were originally looking at thick and low reclaim for the tailings technology when you had fresh groundwater, because you've got cheap, plentiful groundwater. But if we have to go through more work to source the water, then we're going to look at options to reduce water consumption as well. So we're looking at high reclaim, paste thickened, and stack filtered. It also makes a very significant difference to the economics where your mine's located. And because this is a theoretical ore body, we can theoretically put it wherever we want. So for the purposes of this demonstration, we've chosen 2 locations, one proximal to the coast at not significant elevation, and one significant, about twice the distance away at a much higher elevation. Those are continuous variables in the way we've modeled this, so we can just plug in new numbers and look at other locations. So I touched on before, what are our metrics for success? What are we actually chasing here? And typically in a real operation, the company and or the board would have some things they're concerned about, some things they're sensitive to. In the absence of that, being a numbers guy, this has been my full-time role for the last 3 years, doing optimization work with Whittle. I'd say my central premise is that the mine exists. So a reasonable test for, is it going to be financially viable, is the net present value of the operation is higher than the capex. You want to be able to pay to build the mine and make your money back and make it all essentially double your money. So if it costs 2 billion to invest to create the mine, then an NPV of 4 billion over 20 years feels like a reasonable place. But there are obviously plenty of other things to consider. What are we interested in? And water intensity is probably something that's important to the audience I'm currently speaking to, so we will focus on that. But yeah. Now the next 3 slides are going to be relatively high in technical detail. I'm not going to go through it in any significant length. Just wanted to present it to communicate the level of technical work in this model. So this is a block flow diagram of the water balance, things going through the concentrator, the tailings thickener. This is really here to demonstrate that the model is built in parallel with this. So every piece of rock that's going through our theoretical mine, we can see where it's gone, the water that came with it out of the ground, the water that's been added to it, all the water and all the rock mass is tracked. So the water modeling is intrinsically tied to the operation. So when we optimize the operation for value, it sees all the water movements and all the water costs. And this is some of the inputs behind how it's doing that. So we've got density, viscosity, recovery changes for your water type. We've got Laurie's done most of the work behind the assumptions for the tailings, where how easy it is to dewater, the costs related to things like that. So all of this is again a subset of a technical model and an example of part of the calculations. Essentially, every block or similar group of blocks in the model goes through and gets all these details and then finds its own pathway out to the other side. So if this is confusing, that's great. I'm just going to summarize the high-level outcomes of this model, but I thought it was important to communicate that this level of technical detail is in the model and is available as outputs from the model. So this is what we typically call a dashboard, which I'm not looking in this level of detail for this presentation either. This is a summary of a summary. But some important things for this base case would be that the life of mine NPV is 3.7 billion and it costs you 2.1 billion to build. So you're getting your money back and then you're getting 170% of your original investment back on top of that. So look at things like the water intensity, about 200 cubic meters per ton of copper produced, and the size of the mine, the amount of ore processed. Here's your mining schedule. I've given it a fleet of 90 million tons per annum. Here's your material being mined out by phase. There's a full schedule, the stockpile balances, the grades going to plant. All of this is available for other specific technical work, but we won't focus on it today. So now I'm going to step through some of the first order effects. So one that we'll just note quickly is if you do use raw seawater, there's a recovery loss. So not having real metallurgical data for this theoretical ore body, we've decided to use a 1% recovery loss for copper and gold. Obviously, things like molybdenum would change that significantly. So you need to do that work with a focus on your actual ore body. Now, here's a high-level summary of the water-related CapEx. So obviously, you've got to build a water supply pipeline. That varies dominantly with the distance. I've been involved in some projects where you reduce the actual volume of water supplied by the pipeline by 80%, and it only brings the cost of building the pipeline down by 20%. Because for the most part, you're paying for the clearing, the labour, and the sort of work that only matters for the distance of the pipeline. So in our close to the coast case, 240 million US dollars, $500 million when you're further away, just for the pipeline. So desal and water treatment. This is a summary of a few different pieces of the puzzle, but one of the larger pieces here is the desal plant, which when you move to a more water efficient tailings paradigm, you need a lot less water desalinated. So that cost comes down significantly in the CapEx phase. And then this is the rest of the plant infrastructure and the tailings infrastructure. So notably for stacked filter tailings, there's a lot of expensive pieces of kit that you need to add to your process plant and dewatering. Now, it's the quality of the ore body that determines if it can support the CapEx. And we're not just talking about the size of it, we're talking about the grades, we're talking about the metallurgical characteristics, the rock hardness, and obviously things like metal price and the mine location. So this is all traditional first order effects, the sort of stuff you can do in a spreadsheet. Now we move to the operating costs side of that. So this is all the water operating costs related to the supply of water, the treatment of water, dewatering. So we've got desal, which varies dominantly with how much water you're treating. The pumping, which varies mostly with your elevation. There's some frictional losses based on the distance and the pipe, but dominantly it's with elevation and the amount of water you're moving. And then your tailings dam, plant, water treatment. And instead of trying to dig into each one of these specifically in this limited time frame, what I've done is I've aggregated all of those outputs from the modeling work and then divided it by the total external mass of water required. So if you look at the numbers in this way, then you can see in our original case, we're paying 54 cents per cubic meter of water. And if you have a mine site or potential mine site that's close to the coast, then using raw seawater, this is the operational cost, costs you 70 cents per cubic meter, and desalinated seawater costs you $1.06 per cubic meter. Now, this is ignoring the capital costs that we already looked at. So this is just the costs associated with the water on a day-to-day basis over the 19 years of mine life. Now, looking at it this way, you see that this thickened low reclaim is the cheapest option for your water. You're seeing it getting progressively more and more expensive per cubic meter, including out here, you're paying 32 times the cost. And if that feels wrong to you, then you're right, because this is not the right way, in my opinion, to look at your water-related operating expenses. Right here, where we're pricing what does a cubic meter of water cost, and we haven't attached actually how much water are we using. So I've done the same calculation here and divided it by the total mass of ore material. So now we've got a different picture. So if you were looking at it on this basis, how much does it cost to supply water? You'd suggest that this thick and low reclaim is the most financially effective outcome. And when you look at it, how much does the water to process 1 ton of ore cost? We're now looking over here at paste thickened. Just letting that sink in for a second, and I think we can move on. So based on what we've covered, in order to demonstrate first order effects, instead of using this optimization model that we've built, these sort of high level tools, I've taken the original optimized model, which was very well optimized, and stepping through the first order effects one by one manually in a spreadsheet. So based on what we just looked at, decided that I'm going to use raw seawater because desal plant looks expensive. I don't want to build it. And obviously that wouldn't traditionally be my decision. There'd be a board and there'd be other stakeholder engagement. But so looking at raw seawater, and then based on what we were just looking at here, looking at paste thickened tails. Now, I think the case for a location further away from the coast is more interesting. So that's what we're going to look into rather than this one that's at 80 kilometres from the coast. So here, quite a simple change, recovery loss by 1%. So for all of these manual adjustments to the mine plan, I've taken all the outputs from that first base case optimization we created. So it's the same schedule, it's the same trucks doing the same thing, the plant processing the same material. So we can isolate the first order effects. When we drop the metal recovery by 1%, which as mentioned could be more, could be less, we drop about 300 million in revenue over life of mine, and that drops the NPV by 130 million. So we're still in a pretty good place. Like this is not a showstopper at all. So then we add all the capital costs, and dominantly it's the water supply pipeline for $500 million. I mean, there's another $100 million of capital in there, but that's the significant change here. So we see our NPV go down because our capital costs go up, and then the ratio between capital and NPV drops significantly at this point. But this is just to build the infrastructure. We haven't actually paid the additional costs to pump the water to our mine site yet. So let's look at that. And we go from about 240 million in water-related operating costs, which that's what it was going to cost us to use the local groundwater, to 1.3 billion in water-related operating costs. So a lot of that is the energy of transporting the water to site, but it's also water treatment, tails dewatering, and our ability to raise capital to start this operation is looking shaky, because instead of investing 2.1 billion, we're looking at 2.7 billion, and after you get your capital back, you kind of make another 2.6. So it's a less appealing option if there's another mine site around that's offering this. But what I hadn't done on that last step is change the water balance. So moving from thick and low reclaim to paste thickened means we actually require 60% less water. So that operating cost for water comes down in line with that. And this is a traditional approach to a change to the mine plan. If you want to get an idea of the different options, you can do all this first order work in a spreadsheet, and this is where you would end up. So we've got recovery loss, increased CapEx, increased OpEx, and then lower the water requirements, claims most of that OpEx back. We started with a potential operation worth 3.7 billion, and we're down here at 2.9 billion, based on changing our tailings paradigm and our assumption on water source. That is a huge impact on the mining operation, and it's a solid case for why water needs to be integrated into these decisions. So now we're going to have a look at some second order effects here, because our definitions of ore and waste and what's economic to process is just that. It's an economic decision. And we've changed our costs. We've changed our metal recovery. So the plan that we so carefully made the first time round, which probably took our technical team 6 to 24 months, is potentially incorrect now. So what we've done here is, instead of doing all these things in a spreadsheet, we've fed all the updated cost information into Whittle's Proba Optimizer. So it's looking at the exact same pit, the exact same block model, but now that it can see the change in water costs, it's effectively making a different schedule and making different stockpiling decisions. Material comes direct from the pit to the plant at different times and comes back off the stockpile at different times. So it's actually improved the NPV by $65 million with no other changes than a new mine plan. So that is one of the things that is a second order effect. And then, as we just noted, if we've changed the economics of this, then the pit design is probably incorrect now. How incorrect? Well, it depends how much we changed everything. So when I did the original pit and phase work for this in Geovia Whittle with skin analysis, auto pushback chooser. Happy to go into more technical things at another time. But redoing that same work, we end up with a pit that's 7% smaller in total mass, containing 5% less ore. So you re-optimize the pit, and our 19-year mine life is now 18 years, based on just the additional water OPEX costs. So this is only a 40-cent difference for a pretty significant change in the volume of the pit. Now, I've done this work quite a few times, and I know that re-optimizing the pit is definitely going to increase the NPV of the operation. So I was very surprised when it didn't. So I think one of the learnings for me on this was that you have to do the work on each ore body for each operation with the assumptions that you're feeding into that model, because I would have bet my car that the NPV went up significantly from this change, and it didn't. But lots of things did change. Is this an improvement? Well, it depends on your metrics for success. So I was using dominantly NPV, and this is within the modeling uncertainty. There's no financial difference between these two pits, but there's a big significant physical difference. We're making less copper and gold. Well, if your goal is to supply metals for the energy transition, then that's a bad thing. The pit's physically smaller, and it's got a smaller footprint, smaller interaction with the landscape, smaller tailings facility required. That's probably a good thing. Our carbon footprint's down about 8% because a lot of the mass we lost was in the bottom of the pit, which is the most carbon intensive. That's a good thing. We're using less water. I mean, the water we were using in this case was seawater anyway, so how much do we value that water? And compared to the previous paste thicken case, we do have a reduction in water intensity because it's a bit more effective. So visually, the pits are almost indistinguishable. So there's three internal phases, but just looking at this outer phase, for the majority of the skin of the pit, we're only moved it by one block. But it matters. It makes your mine 1 year shorter. Is that the metric that you're measuring by? Did you want to create jobs and stability in the area? So here's looking at that left to right, the sort of focus case here that we stepped through. So adjusting the recovery, CapEx, OPEX, water balance, reschedule, and new pits. So we're in pretty similar case, pretty similar place. But it got stuck in my head pretty quickly. If we've only changed the economics here by 40 cents a tonne, and the final pit changed by 7%, then what happens if we're looking at a stacked filtered case over here with desalinated seawater? How much does that move the pit? Well, so it did the work, and you drop about 16% of the pit mass, 15% of the ore, make 12% less copper, and you end up with a significantly smaller pit. So there may be reasons that desalination is the correct way to go. It may be that the metal prices move such that your NPV comes up significantly and you can afford that. What are you making your decisions on? What's the goal? So the next few slides are just a bit of a summary of those pieces that we've discussed so far. So this is stepping through that worked case that we've just looked at. And here's an optimized case for the new pits. Now, I think if I had this side by side with the first one we looked at, it would be be difficult for most of us in the room to point at what's changed specifically. But because it's hard to discern doesn't mean it wasn't important. Now, Philip, I think we're getting close to a place where we're going to invite conversation around this. But
Yeah, I'd
Sorry.
encourage everybody just to put their hand up. I noticed Mohammed put his hand up earlier, so you might want to put it up again and ask a question. But yeah, from about here onwards, please interrupt and start asking some questions.
So what we're looking at here.
Mohammed does have a question in the chat if you wanted to answer that one.
Okay. Yeah, I'll answer that one, Bill.
Sorry, I'm not being coy. I was trying to eat dinner at the same time, so I figured I'll put it in the chat.
Yeah, no
Thanks,
worries.
Mohammed. Laurie, you want to take that?
Yeah.
Laurie, did you want to answer that question? Did you say? Or?
Oh yes, I can answer it in the chat, or I'm just looking up what our costs
okay.
assumptions were. Yeah,
right.
Just a general comment. Like these costs don't take this as, if you like, an engineering study, if you like, right? What we've done is we've taken some reasonable placeholders on what some of the costs are. There are definitely cost differentials. We did look in some detail into the pumping requirements, but there are costs, for example, associated with corrosion that can increase piping material costs, that can potentially increase some maintenance costs. So I don't know if we really went to that granular level, to be honest, Mohammed. I'm just checking what assumptions we did
That's
put
okay.
in. But, yeah.
No, that's okay, Laurie. The reason I asked a little bit was when I saw the resolution on 1% recovery loss, I said, okay, we're getting into quite a level of detail. So I thought we were getting into those percentages. But in the conclusion, when we talked, I think when Greg was talking about if the objective is to produce metal for a transition economy, then scenario A versus scenario B, which has smaller footprint. The other factor, I'm assuming, as soon as you're in Chile and you're looking at desalinated water, it means you're probably in a dry, arid area. As soon as you desalinate water and pipeline it over, you might just become a water producer for an area that doesn't have water. So now you've produced a different secondary benefit.
Correct, yeah.
And then would that be
that's
factor? Okay.
That's a consideration, because if you're just looking at this from the perspective of what the mine needs, that doesn't potentially include the benefits of, for example, the infrastructure and the other users. So that's, I think, to the point of the third order effects that Phil and Craig were referring to. So it's not necessarily the entire picture that we're showing here, but part of what we're trying to do is to show that there are multiple ways in which costs or revenue adjustments and benefits can appear, and trying to demonstrate that the modelling approach allows you to incorporate those things. The factors may change, the magnitude of some of those may change by deposit.
And the questions are not trying to get into the specifics here, but I would almost, in a scenario, I would argue some of those are actually first order costs or first order, because for you to get a pipeline in those arid areas, you may have to form an agreement. You may have to give some water takeoff. So you may have to build or pipeline cost of water, maybe 20% going to the communities as part of your social license for you to have that pipeline. So therefore, it comes off your direct bottom line, or it's your cost of doing business, otherwise no mine. But again, not to debate here and there, but I like where you're going of taking scenarios of modeling front end and all the way down the back end to optimize the whole system, which is, I think, the purpose of the study.
Yeah.
So, Mohammed, that's a pretty cool question, and we've got a slide right at the end, which is what the hell next slide, and that might actually. We didn't include that particular one on the what the hell next slide, so thanks for raising that.
Well, this is what happens. You get a bunch of engineers on a phone. We just start trying to dissect everything.
Yeah, thanks.
Yeah.
Okay.
But to answer the original question quickly, we did discuss the corrosive nature, but we didn't have any clear idea on how much that would raise the maintenance costs. So it wasn't considered in this model. But if you have numbers around it that you'd like to put forward, we could consider it in future works. I think one of the points of this presentation, as Philip just suggested, is to show that we have this model, this chassis to do future works. So if there's a piece of this that you're interested in, by all means, let's have a look. So what we're looking at here was getting Proba to re-optimize all the cases for close to the coast. So we've got this original case here that we're comparing things to, and then the 4 different tailings paradigm with raw seawater, the 4 different tailings paradigms with desalinated seawater. So this is the same data down the bottom, just the NPV represented graphically for people who prefer pictures. Now what we're seeing is that in a location that's close to the coast, your water transport costs aren't too onerous. Then there's no significant financial case between these 3 tailings paradigms in a raw seawater case. They're all sitting in the same space financially. So the suggestion would be that you'd still move to paste thicken, given the inputs that we used for this model, on the basis of water intensity. But you need to, as a company, be engaging in those other metrics rather than just looking at the finances for that decision. That becomes clearer when you look at something further away from the coast. You are seeing a financial benefit for this less water use, and seeing the water OPEX at $1 billion, mostly to transport enough water to run it this way, and you halve that if you move to paste thickened. Just a high-level summary of both there. Yeah, so mine optimization is complicated and ideally dynamic, and I went into this with full control over the ore body and the mine design, and still surprised myself at a few points throughout the process. So my major personal takeaway here is that you just have to do the work. You have to do the work for that ore body in that location with the appropriate costs.
Thanks, Craig. You segueing back to me here. So I'll throw the floor open to discuss the work before we look at future work. Thanks to Mohammed for that first question. Anybody else want to make a comment, or Steve?
Yeah, just had a quick question about mine closure costs. Is that something you've looked at all? Because I think there might be some story that rehabilitation of tailings storage facilities is easier if the content of that facility is drier. Has that been looked at all?
So mine closure in this context was part of the mine capital, and we didn't vary it on a case-by-case basis. So if you've got information to improve the model, I'd love to hear about it.
I don't.
Yeah, I think that's part of, that's part of future scope. It's a good question, and not necessarily coming from Steve, but I think it's a general comment that is valid, and also one of these aspects around the bigger picture of sources of value, if you like. I think one of the issues that we are grappling with a bit, Steve, is there's kind of these qualitative or they not yet quantified out of scope pieces, and what's next on the radar. So I think Phil's going to talk about some of the more immediate things that are on the agenda for this type of modelling. And then I think there's probably some parking lot type of issues like the one you've raised that also, ought to be considered in the big picture, but might be a little bit out of scope of some of the initial work we're doing. It might be a bolt-on from other parts of the GWI, if you like.
Sure, got it. Thanks.
Thank you, Steve. Nice to hear from you. And our Eagle's written a semi novel on the bottom of the comment there, so we might go to Mario first. Mario, you got your hand up, and
Well, it's a more broad question. Thank you for the presentation, presenting on the result from the Neo-Marvin case. Now, how do we plan to publicate and make those results available to the public, and to make it as available not only tonight but to other people interested to look at it? When and how?
I could probably take that. The idea of Seek is that it is made generally available. So this presentation will go onto the website. You'll take care of that. Where obviously the first presentation was also lurking. So if you were on this story and you didn't listen to the first one, there's a little bit of extra in that for you. So I think that's
Philip, you're breaking out.
Oh, you can't hear me?
Now I hear you. Yeah.
We can
okay
hear
now.
you.
It's been a bit croaky for the whole voice. It's getting worse.
Disjointed.
Okay, it's not my
Maybe
voice.
just-
It's my Bluetooth connection, unfortunately.
Okay.
Yeah, it's not a bandwidth problem. It's my Bluetooth connection. I'll hopefully you can hear me. I'll speak a little slower. Yeah. So the normal way, and we do have in mind a podcast as well on this topic. And of course, we do want to talk to people about extensions to this work, which we might move to in a moment. Yeah, thanks, Craig. Igor, did you want to say something, or are you happy for the chat comments?
I just put it in the chat
okay.
I knew it was going to be larger feedback, so I just write it down so Mohammed can take a look later, and everyone else.
Okay.
And same with the other one on corrosion in the pipeline. So I'm just also adding some regional view on that one.
Okay, thanks, Igor. So feel free to keep asking questions on, but I will go through the slide. I did want to make sure we do this before the top of the hour. So what can we tackle next? And the team, alongside Laurie, who's the Seek connection on this project, we've been debating what to suggest here. So here's some suggestions for the wider audience. So using what Craig has currently built, we could do a number of things. There's adding variation to grind size, which is what is represented by that GTR, grind throughput recovery. We could look at something to do with acid generation, so PAG versus NAG options. Would you like us to go to a different climatic location? So not an arid Chilean style example. We could go, for example, to Canada. I don't know where we would put our porphyry copper gold in Canada, but something akin to that.
It would be in British Columbia.
British Columbia, there you go. Yeah, we would. We like also the idea of is that penalty of 1% that we put in there just because it was seawater. What happens if it's much worse than that? And that would be true if we had moly in the ore body. And then there's always the copper and gold price variations we could do. Yeah, another click. Thanks, Craig. Other things we could look at would be technology or flow sheet options, such as pre-concentration. I've mentioned here coarse particle flotation, which has been bandied around by a few people. And I've always had a little inkling that Anglo's hydraulic dewatered stacking might have some sort of role to play in the model. And I think I'd love to go in that direction as well. So that's using the current model. Then there's another sort of parallel option that we think to use an existing operation and depleted ore body and looming restrictions. So in this one, we did a very simplistic, you can't use the continental water anymore. But we could expand that aspect. Do we have to close? Should we go on care and maintenance for a while? Scale back, change supply. There's a more detailed version of that story to tell. And then on top of A and B, as we move forward, we're also have in mind that the ultimate objective of this is to really understand how water and the life of mine planning procedures and activities go on, to link them even more closely. So how do we take hydrological models where we're concerned with the catchment footprint, the rainfall, rivers, perhaps river diversions, even pit boundaries encroaching on lakes or rivers, and pit dewatering? All of that is also important, and we could move towards that as well already. I would suggest, I know Craig's really eager to get that far, but the importance of, I know that Claire Coate is not on the call. I think she told me that she wouldn't be able to, but her comment to me a couple of weeks ago was, we hydrological people do a wonderful job of understanding the water supply situations, either from groundwater, pit dewatering, or the surface water catchments. And then the mining engineers go and change the mine plan. We have to do it all over again. So that comment tells me that there's space to move towards making sure that hydrological modelling can be in some way linked to life of mine planning. And I guess that's the original hypothesis, was can we move to get that far? That's where we'd like to go eventually. And then D, just to finish off, I think that in the further future, the far future, is do we need a Marvin equivalent that is not copper or copper gold? Is there another commodity? I would hope that would be simple, but I think we're thinking a little bit further. So we've got some options here, and sponsors who might be interested in throwing a little money in the pot to take it further would be welcome. So use the existing model, do a little change existing operation, or march on towards the hydrology models is the options that we see in front of us. Anybody got other ideas or comments on those? Oh, Eric, I see you ready to speak.
No, I'm good, Phil.
Okay.
I think number A, I think that, we talked about that a little bit. Combining the CPF and the HDS together, I think that could be essentially that would put meat to the bones of the value proposition that we think is there. But with a model system, I think that would be very valuable.
Yeah, I think the premise out of the Whittle camp is you may well have a technological suggestion, and you value it with a first order, CapEx, OpEx, exchange this, drop that out of your flow sheet, put this one in. All of those things happen at a first order readily. But we would feel the second order effects can't be calculated by a vendor
No.
And therefore, are they second order effects? Are they material? In which case that might revalue the technology. I think that's the conversation you and I had about this. That's really the synopsis of that. Laurie, you've got your hand up.
Yeah, just to comment. I mean, that's certainly an area of interest, Eric. The qualitative premise is that these types of approaches will improve water management, reduce water use, etc. One question really is how to balance, confidential and proprietary data with an approach where we're trying to make things public. So I know there's some stuff in the public domain. I think having companies like yourselves providing what you can from things in the public domain, this approach of using realistic but not real cases, like a simulated plausible ore body, combine that with a simulated but plausible tailings facility, and somewhat representative data coming out of coarse particle flotation information in the public domain, I think that could be quite workable. There may be more sort of specific spin-offs where companies want to do this on a particular site. That's a bit different, right? Because that will be more specific test data related to that site. But I think anything we can do to manage that, you know, how we can use realistic data sets and incorporate it into this would be, you know, really worthwhile.
Yeah, well, one thing that's, I think it's the combination of CPS and the hydraulic dry stacking, and we do have the advantage that in the second technology is also owned by an operator. So, you know, perhaps Anglo, in the interest of testing this out on something that they're working on that they have in their portfolio, it would further two aims at the same time. So really should talk to the guys at Anglo about that, because I think it could be a powerful, and even if you can't do an actual system, I think the synthetic model system has a lot of value.
Just a quick question out of interest: is there a grind size data for this body?
I think there is, isn't there, Craig? We just haven't activated in this case as yet. So that first one in the left-hand box, GTO, is. Sorry, Craig, I'm taking your thunder here. What's your answer?
That's fine, Philip. Yes, we do have simulated grind size data for this operation. So we've got recovery changes and energy cost changes, and therefore throughput changes across, I think it was 5 grind sizes, from I think as low as 75 micron, maybe 106 was the bottom end, up to 250.
That's P80, is it?
Yep.
Okay, right, thanks.
And in the scope of work that we've done so far, we actually had the grind size locked to 125 micron. So that was not part of this optimization that we've presented today.
Okay.
It routinely is in the Whittles work, of course, and but we had a limited scope. I see that we're right up against the top of the hour here, so I'm going to call it there, but we'd happily engage. I think we should just acknowledge some of the sponsors here. So we've questions from both Agnico Eagle and Weir today. So thank you very much, guys, for your support, not only with the questions, but the injections of some funds. The Grantham Foundation have been extremely generous as well. So thanks to them. And we the Global Water Initiative in its entirety has got some great partners in the research area with the University of British Columbia, as well as the Sustainable Minerals Institute at UQ. And even though I'm from Whittle, I also wear a SEEK director's hat, so I will thank Whittle Consulting for their in-kind contribution on this study. If you'll allow me a little bit of license to do that. Thanks everybody for coming along. Thanks to those who might be listening later as well. And if those people have got some questions, I think you know how to find us, and we'll be happy to respond. Yeah, so that's it for now. Thanks very much. I'll call it there.
Yep. Thanks very much, guys. Nice to meet you all virtually again.
Thanks, great. Great job.
Thanks, Eric.
See you.
Thank you.
Thanks, everyone.
Bye.
Bye.
I'll let you stop the recording, Jill, if you like.